Hello everyone, you are welcome to today's class. Our topic today is dimensional analysis. In our last lesson on dimension, we saw how dimensional formula is used to express the unit of physical quantities in terms of the fundamental quantities. That is m for mass, l for length, and t for time. Dimensional analysis is used to check the accuracy of formulas. It's used to determine the relationship among physical quantities. It's also used to determine the dimension of physical constants. One limitation of dimensional formula is that it does not determine the uniqueness of physical quantities because work, energy, and torque have the same dimension. Consequently, the same derived unit if broken down to the three basic fundamental units. Let's take a few examples on dimensional analysis. Example 1. The force F acting on the wings of an aircraft moving through air of velocity v and density ρ is given by the equation F is equal to k v raised to power x ρ raised to power y a raised to power z, where k is a dimensionless constant and a is the surface area of the wings of the aircraft. Use dimensional analysis to determine the values of x, y, and z. To find x, y, and z, we first of all state the formula we are given. F in square bracket is equal to k, v in square bracket raised to power x, ρ in square bracket raised to power y, and a in square bracket raised to power z. They are written in square bracket. We should not forget that this is dimension. So we'll write out the dimension of each of the physical quantities. F now, the dimension for F is mass times acceleration, will be mL t raised to power minus 2. K will disappear because it has no dimension. So we'll have L t raised to power minus 1 all in bracket raised to power x. mL raised to power minus 3 all in bracket raised to power y. L square all in bracket raised to power z. We are looking at the right hand side of the equation. So we'll open the bracket of the three terms we have in the equation there. We'll now have L raised to power x, t raised to power minus x, m raised to power y, L raised to power minus 3y, L raised to power 2z. We'll now collect like terms together. We start with m. We have only one m on the right hand side of the equation, which is m raised to power y. We have three l's, l raised to power x, l raised to power minus 3y, and l raised to power 2z. Putting them together, we have l raised to power x minus 3y plus 2z. We have only one t, which is t raised to power minus x. Now we are going to compare the left-hand side of the equation with the right-hand side of the equation. The left-hand side of the equation, we have m raised to power 1. And on the right-hand side of the equation, we have m raised to power y. In that case, we will have m raised to power 1 is equal to m raised to power y. So 1 will now be equal to y. Therefore, y is equal to 1. On the left-hand side, we have t raised to power minus 2. On the right-hand side, we have t raised to power minus x. So we have minus 2x will now be equal to minus x. We multiply both sides by minus 1. We have 2 is equal to x, and that will give us x is equal to 2. On the left-hand side, we have L raised to power 1, and on the right-hand side, we have L raised to power x minus 3y plus 2z. We are going to substitute value for y and x. So we have 1 will now be equal to x minus 3y plus 2z. When we substitute in for x, which is 2, and y, which is 1, we'll have 1 is equal to 2 minus 3 plus 2z. And 2 minus 3 will give us minus 1. So we have 1 is equal to minus 1 plus 2z. Minus 1 we move to the other side, collecting like terms together. Then we have 1 plus 1 is equal to 2z. 2 will now be equal to 2z. Therefore, z is equal to 1. X is equal to 2, y is equal to 1, and z is equal to 1. So writing this equation correctly, we have f is equal to k v raised to power 2 rho and capital letter A for area. That will be our correct formula for that equation. Example 2. The effective potential energy E of a lunar satellite of mass m1 moving in an elliptical orbit around the moon of mass m2 is given by E is equal to k square over 2m1 r square minus g m1 m2 over r, where r is the distance of the satellite from the moon and g is the universal gravitational constant of dimension m raised to power minus 1, l raised to power 3, and t raised to power minus 2. Determine the dimension of the angular momentum k of the satellite using dimensional analysis. To find the dimensional analysis of k using the formula E is equal to k squared over 2m1 r squared minus g m1 m2 over r. 2 is a constant, it has no dimension, so it will just disappear. Each of these terms have the same dimension. That means the dimension of energy is equal to the dimension of k squared over m1 r squared. The dimension of energy is equal to g m1 m2 over r. And that in that case, that means k squared over m1 r squared will be equal to g m1 m2 over r. Their dimension will be equal. So you can pick any of these equality to solve for k. But you are asked to find k and you are given the dimension of the gravitational constant. That means they are interested in the gravitational constant and they are interested in you finding k. It's advisable for you to now take k squared over m1 r squared is equal to g m1 m2 over r to find the dimension for k, though that is a longer process. So to do that, you will break each of these terms to their dimension. K, we are looking for the dimension, will now be k squared divided by the dimension of mass m. The dimension of r squared will be l squared, which is equal to substituting the dimension for the gravitational constant, m raised to power minus 1, l raised to power 3, and t raised to power minus 2. The dimension for m1, m2 will be m squared, and the dimension for the radius r will be l. So the next thing we do, let us cross multiply to get a linear equation. We'll now get k squared l will now be equal to m l2 m raised to power minus 1, l raised to power 3, t raised to power minus 2, and m squared. M and m raised to power minus 1 will take care of each other, so they will go away. And let's combine l raised to power 2 and l raised to power 3. We'll now have l raised to power 5, t raised to power minus 2, and m raised to power 2, which is equal to k squared l. So k squared, we were looking for k squared. We divide both sides by l. So when we divide both sides by l, we have k squared is equal to l raised to power 4, t raised to power minus 2, and m raised to power 2. We'll now find the square root of both sides. We'll now get k is equal to l squared, t raised to power minus 1, and m. Let's rearrange this so that m will come first, l will come next, t will come last. In that case, we'll now have k is equal to m, l raised to power 2, and t raised to power minus 1. I hope you enjoyed the lesson. If you have any question, do not forget to drop them at the comment section below and I will respond to them as soon as possible. Do not forget to subscribe. Bye.